In this video, let's take a look at solids of revolution. The next type of volume we'll study in calculus is obtained by revolving a defined region around an axis. The axis might be the x-axis, the y-axis, or a horizontal or vertical line somewhere in the coordinate plane. There are two types of volumes of revolution. One uses the disk method and the other is the washer method. Let's take a look at both. So the disk method is where you have a solid figure. The cross section is a solid disk, and it's a circle. And so if we're finding the volume, it's going to be the integral from a to b of the area of the cross section, which is a circle, and so therefore it's pi r squared. And then since it's our representative disk is vertical, it's going to be dx. So let's take a look at our first example. We have region R is bounded by y equals e to the x, which is this slope right here, this graph right here. The x-axis, x is 2 and x is 3. So this is a nice diagram, and so you can see here is our representative disk. What is the volume of solid created when R is rotated around the x-axis? All right, so let's set up our integral. So our volume is going to be from 2 to 3 of this disk, and we need to find the radius. The radius is created by the top function, e to the x, minus the bottom function, which is just the x-axis. And so that's just going to be, let's go ahead and write that out. So my radius is created by the top function minus the bottom function. And so, and we know the formula for our circle, pi r squared. And so pi times the radius squared dx. And that's all it is. Okay, so usually what we'll do is we'll go ahead and factor out the pi, and then e to the x squared dx. We'll take this to a calculator to actually evaluate that. And so I think I put that in my Desmos already. Yeah, it's this very first equation, line 1. Here's my pi, and I put it inside. It doesn't really matter. E to the x squared dx is going to give me a volume of 547.94. I went ahead and just put it in just to save time. So volume is 547.94, and that's units cubed, whatever those units are. So again, the radius is created by the top function minus the bottom function. In this case, that was e to the x minus 0. And the formula for the circle is pi times the radius squared, so that's why I squared it, times dx. And here it is again. The horizontal axis of revolution was just the x-axis. All right, so here's our second example. We have region R is bound by y equals x cubed minus 2x squared, y equals 10, x equals 0, and x equals 2.4. So we know we are between 0 and 2.4, somewhere over here. And it says, write but do not evaluate an integral expression to find the volume of the solid created when R is rotated around the line y equals 10. So I'm going to be rotating around this line. That's my axis of revolution. I'm going to go ahead and see if I can sketch out what this is going to look like. It's going to look something like this, and it comes up, and then roughly like that. So here is going to be my representative disk. Let's see if I can, here's my disk. And so we can see that my radius is going to be created by the top function minus the bottom function. My top function is the cubic function. My bottom function is the line y equals 10. Whoops. So volume is equal to pi. My interval is between 0 and 2.4 of the top function, which is x cubed minus 2x squared, minus the bottom function, which is 10. So pi times my radius squared dx. And I went ahead and I did calculate it. You don't have to, but if you want to, you should get in your calculator. It's this second one here, and Again, I put the pi on the inside. In the third example, I actually pulled the pi out, but it's about 817.606 in your calculator. And to get that integral sign, you just type in INT, and it should show up. So volume is approximately 8117.606 units cubed. All right, and here it is again. In this, when I worked it out previously, I found my radius down here. You'll get the same answer. If you take 10 as your top function minus this is my bottom function, you'll get the same answer. All right, so this method to find the volume of a solid of revolution was in the previous examples. We've had vertical disc, representative disc, so they were in terms of dx, but they can also be horizontal. You can have a representative horizontal disc, and they would be in terms of dy. So the second method is the washer method, and when you rotate your region around an axis and the figure generated has a hollow section, this is the washer method. That means the representative will have a hole, which makes it look like a washer. So when we find the volume from some interval from A to B, we need to find the area of the outer circle and minus the area of the inner circle, dx. And so it's going to be pi r squared. R is going to represent the bigger circle minus pi r squared with the little r representing the smaller circle. And r squared, we've got to square the r's and then take the difference, dx. And so if you factor out the pi, it's just going to be the interval from A to B of r squared minus little r dx, where capital R is the outer circle and little r is the inner circle. So let's take a look at some examples. Here's the first one. And when we rotate this figure around the x-axis, it's going to look like this. So we'll have this big like hollow space in the middle. Okay, so let's get started. My bigger radius will be created right here. This is going to be my big R, and then from here to here, this is going to be my little r. All right, and I'm going to go ahead and write my interval. It looks like we're evaluating from 0 to 1, and square root of x minus 0 squared pi times the radius of the big one, which is a square root function minus the x-axis squared, and then minus the little radius minus 0 squared dx. Okay, so we can definitely clean this up a little bit. So this is going to be pi times the interval from 0 to 1, and if we subtract 0, of course, is nothing, but when we square the square root, that's going to just give me x. And over here, this minus 0, of course, is x squared. Squared is going to be x to the 4th. So this is going to be minus x to the 4th dx. And this one we can do pretty easily. If we differentiate, that's going to give me x squared over 2 minus x to the 5th over 5, and we're going to evaluate from 1 to 0, and so this will give me pi times 1/2 minus 1/5, and then minus 0. So pi times 1/2 minus 1/5. If I get a common denominator of these two guys, that would be 10, and so this would be 5/10 minus 2/10 multiplied by pi, so this is going to be pi times 3/10. And this is volume, so this is units cubed. And here it is again, worked out previously to make sure I'm doing this all right. All right, here's another example. This time we have a nice big open area in the middle. The region bound by y equals x squared minus 2x, which is this parabola here, and y equals x, which is this linear function in red, is rotated around the line y equals 4. Okay, so first let's draw in our radius. So here's the radius of my outer circle and the radius of my inner circle. That's little r. And it looks like our interval is between 0 and 3. So volume is equal to pi 0.03 of the outer radius, which would be, and top function minus the bottom function, so this would be 4 minus x squared minus 2x squared. That would be the radius, top minus the bottom squared, and then minus the inner. So this would be 4 minus x squared dx. We can clean this up a bit, distribute the negative in that first set of parentheses, but pretty much I'm just going to go straight to Desmos, and we can plug it in. And I believe this is the last one I plugged in, and you can see in line 3 I did go ahead and distribute the negative, and just when you're putting in, make sure you're squaring both of those. I also expanded the second parenthesis, the binomial 4 minus x, and that's why we have 16 minus 8x plus x squared dx, don't forget the dx, and we get about 96.133. So my volume here. If you're going to use a calculator to evaluate, I would not simplify, I would just stick it in just like that. And here it is. And you can see here's where I did the distributing of the second binomial to get that. You can distribute this if you wanted to expand this out, but I didn't. All right, here's our next example. It says, consider the region in the xy plane bounded by y is equal to x squared minus 4. So that's going to be this parabola here, intersects at -4. X equals 1, so that's this vertical line here. And y equals 5, which is this horizontal here. A solid revolution is formed by revolving the region around the y-axis. So this time, our representative rectangles are horizontal. So my outer is going to be this guy, and my inner is going to be, my inner radius will be this guy. And so when I write my integral, they need to be in terms of y. And because horizontal disk have a dy. All right, so let's come up with our integral. So first thing, let's solve for x in both of these, because they need to be in terms of y. So if I have y equals x squared minus 4, add 4 and square root it. So x is going to be the square root of y plus 4, and then oh, and it's right there. How nice. Let's write our integral. So we're going to have from 0 to 5, and my volume, pi times the radius, the big radius, is going to be y plus 4 minus 0, if I want to consider the y-axis, squared, minus the inner radius, which is going to be just 1, minus 0 squared dy. And so my volume, I'm just going to clean it up a little bit, will be y plus 4 squared minus 1 dy. And if we take that to Desmos, I don't think I put it in, so let me go ahead and show you that one. All right, so type in the letters pi, that'll get you the pi, and then int for integral. We're going from 0 to 5, and this is going to be square root of y plus 4 squared minus 1 squared, or just 1, and then don't forget dy. 86.394. Approximately 86.394 units cubed. All of our answers for the AP test will be to 3 decimal places. And here it is again. All right, here's just another example that I've already worked out for you. It says, let R be the shaded region in the first quadrant enclosed by the y-axis, the graphs of y equals 1 minus x cubed. So this is just a negative cubic function shifted up 1. So that's what this intersection here is. This guy, this is 1. And y equals sine x squared as shown in the figure. Here's y equals sine x squared. Careful, it's asking for the area. So the area is just the integral from, oh, and got to find this. So take both of these equations to Desmos, find that intersection, and write it to 3 decimals. If you're using a TI calculator, you would store each of these values as like an A and a B unit, and I'll show that to you later as we are reviewing. And so from 0, the y-axis, to this x value, that's our interval, and top function minus the bottom function. So 1 minus x cubed, and I should have parentheses around that, minus the bottom function, sine x squared. Oh wait, no, I don't need parentheses. Sorry, I don't know what I was thinking. That's fine. Top function minus the bottom function, dx. This is the area. This represents the rectangle, the height of the rectangle, and this is the base of the rectangle. And so in Desmos, that gives you 0.534. And I should put units cubed, though. I'm sorry, units squared. Dang, sorry. Area. So in this example, part B, it says a horizontal line y equals k is drawn through the point where the graphs intersect. So I'm going to go ahead and draw this horizontal line. Y is equal to k. Find k and determine whether this line divides R into 2 regions of equal area. All right, so what we do know is that this intersection point is 0.765, 0.552. We need that because this time we're going to have horizontal rectangles. Okay, and so we need to write each of these equations in terms of y. So we need to solve for x in both of these. So let's do that first. Okay, so I have y is equal to 1 minus x cubed. If I solve for y, I have y minus 1 is negative x cubed. Divide by negative y plus 1 is equal to x cubed, and we take the cube root. So this guy is negative y plus 1 is equal to x. All right, and then in the second equation, y equals sine x squared. All right, to undo sine, we do inverse sine. So sine inverse of y is equal to x squared, and then we square root. So x is equal to the square root of sine inverse of y. All right, so now they're both in terms of y. And we want to see if these areas are the same. So the area of the top region, I'm just going to look at this guy right here, is from this y value, 0.552, up to 1. So 0.552 to 1, and the right function minus the left function. The right function is this guy in terms of x. So this will be the cube root, negative y plus 1 minus 0 if you want dy. And then we'll take that to Desmos. And then the area of the bottom goes from 0 to 0.552, and that is the right function minus the left, the inverse sine of y, minus 0 dy. And when we take these both to Desmos, we get for this first one 0.257 units squared, and for the bottom one 0.276 units squared. And so find k. Okay, well, if we want to find k, we need to set these intervals equal, and we can solve. No, we already found k. K is the intersection, sorry. We know k, so we can find the area, and so we can see that these areas are not equal, so we can say no. These areas are not equal, and here's my work. And there it is, again. All right, so the last thing is find the volume of the solid generated when R is revolved around the line y equals -3. All right, last example. So I'm going to draw in this line y equals -3. See if I can draw that straight. Close enough. And since I'm finding volume, I'm going to have vertical rectangles, and this guy is going to be my larger radius, and this guy is going to be my smaller radius. And my volume is going to be pi times, and I already know the intersection point from those last two problems, which was 0.765, comma 0.552. So from 0 to 0.765 of the outer radius, and this is top minus the bottom function, so this is going to be 1 minus x cubed minus a negative 3. This will give me my radius squared minus, and then the smaller radius, which is the top function, minus the bottom function, and this is dx. Okay, and we take this to Desmos and we plug it in, and we should get a volume of approximately 11.841 units cubed. All right, that's it, guys. There it is. One last shot. Okay.